Okay, so we have a block at 0.5 kilograms going at 26 meters per second, and we have a 5 kilogram ball at the end of a table 1.2 meters above the ground. And so the ball is given an impulse by the moving block, and this graph shows the total impulse given as a function of time. And we want to figure out determine the total impulse given to the ball. Well, first we gotta go and talk a little more about impulse. Newton's second law states that net force equals mass times acceleration, m times a. So m's mass and a's acceleration. So mass times acceleration is equal to mass times the change in velocity over change in time, which is acceleration. So the force is equal to mass times change in velocity over change in time. So from that we can get that the force is equal to m delta v over delta t. And we know that mass times the change in velocity is equal to the change in potential, momentum, and we can just say that the force is equal to the change in momentum over the change in time. And if we isolate the change in momentum, which is impulse, we get that the change in momentum, aka impulse, is equal to force times the change in time. And that is why the graph, we can find the total impulse by finding the area, because when you find the area you multiply the base times the height of the object. And so with time being the base and force being the height, if we find the area under the curve, we'll be finding the total impulse of the ball. Okay, here are some important units of measurements to remember and understand. Force is in newtons, times in seconds. Impulse is in newtons times seconds. Momentum is also in newtons times seconds. Velocity is meters per second, and acceleration is meters per second squared. Okay, so if we want to find a total impulse, we have to find the area under the curve. And if we split this curve into 3 separate parts, we get 2 triangles and a rectangle. So the area of the rectangle plus the area of the 2 triangles will equal to the total impulse, J. And so as you can see, there's 2 triangles and a rectangle there. And the 2 triangles have a base of 4 seconds and a height of 2 newtons. And the rectangle has a base of 2 seconds and a height of 2 newtons. So first let's find the area of A, which is a triangle, which is 1/2 times base times height. B is the base and H is the height. So with that equation you plug in and you get 1/2 times 4 times 2, which is equal to 4. Correct? And the area of C is the same triangle, so we just do the same exact formula and plug in, and we get an area of 4. And the area of B is 2 times 2, because you see the rectangle and you can see that it has a base of 2 and a height of 2 also, so 2 times 2 is 4. And so we said that the area under the curve is equal to the total impulse, which means that area of A plus area of B and C is equal to total impulse. And we just plug in A, B, and C, which is 4, 4, and 4, and 4 plus 4 plus 4 is equal to 12. So the total impulse given to the ball over the 10-second time period is 12 newtons times seconds.
In part B, we are asked to determine the horizontal velocity after the collision. We can find this by using the equation J equals delta P, or impulse, equaling change in momentum. Because we found the impulse was 12 in the previous part of the problem, we can substitute J for 12 and substitute delta P for momentum final minus momentum initial. Because we know that momentum equals mass times velocity, we can exchange the P for m times v. So we get a new equation of 12 equaling mass times velocity final minus mass times velocity initial. Because we know that the mass is 5, we can exchange m for 5. We are solving for Vf, so we leave it the same, and we can exchange velocity initial for 0 because initially the object is not moving. So we get a new equation of 12 equals 5Vf minus 5 times 0. With the new equation 12 equals 5Vf, we get a horizontal velocity after the collision equaling 2.4 meters a second. In part C, we are asked how far the ball will launch horizontally from the edge of the table. To do this, we must use kinematics. So we use these two kinematic equations. Delta x equals v naught t plus 1/2 at squared, and delta y equals v naught t plus 1/2 at squared, where delta x and y equals the distance, v equals the velocity, t equals the time, and a equals acceleration. We must first make a chart showing the variables for x and y. Velocity initial in the y equals 0 meters a second. Acceleration in the y is negative 9.8 meters a second squared. Delta y equals negative 1.2 meters in the y. And we don't know t. In the x, velocity initial equals 2.4 meters a second. Acceleration equals 0 meters a second. Delta x, we don't know. And we don't know time. Because we have 3 known variables in the y direction, we must use this in an equation to solve for t, because t is both common in x and y. We must then use the equation delta y equals v naught t plus 1/2 at squared. Next, we substitute all the numbers we have for the variables. So negative 1.2 equals 0t plus 1/2 negative 9.8 t squared. We are left with the equation negative 1.2 equals negative 4.9 t squared. We are then left with 0.245 equaling t squared. By taking the square root of both sides, we are left with a time of 0.49 seconds. Because t is a common variable for both x and y, we can place 0.49 seconds in the chart for x and y. Now that we have 3 known variables in the x direction, we can solve for delta x. So we use the equation delta x equals v naught t plus 1/2 at squared. We substitute all the variables for the numbers that we have. So delta x equals 2.4 times 0.49 plus 1/2, 0 times 0.49 squared. We're left with the equation delta x equals 2.4 times 0.49. And we get a delta x of 1.19 meters. And that is how far the ball will be launched horizontally from the edge of the table.
That's all, folks.